Sound is okay. Hello, everyone. Good evening, everyone in Asia. Good afternoon, everyone in Europe. Good morning, everyone in America. Welcome to the Pre-RGD32 online workshop. I'm Li-Shi from Gyeongsang National University, South Korea, chair of this workshop. Let us start the Pre-RGD32 online workshop now. Let me introduce our co-chairs. First, the chair of the IAC, Domenico Bruno. Are you here?
Welcome.
Yeah.
Hello, welcome everyone. Thank you for being here.
The co-chair, Dr. Kung Soo from Hong Kong.
Yeah, hello. Hi.
You are here?
Yeah, I'm here.
Yeah.
Hello.
The co-chair, Jong Shin-woo from Taiwan. So can you hear your voice?
Okay. Hi, everyone. This is Jong Shin from Taiwan. Nice to be with you tonight here. Okay, thank you.
It is our greatest pleasure to welcome all of you to this workshop. The recent hot topic in the rarefied gas dynamics. The plan for this workshop began last December when we decided to postpone RG32 to the next summer due to the COVID-19 pandemic. Along with the IAC members, the LOC decided to hold the online workshop this July. We are very grateful from the warm response from the RGD community. We received 26 countries in the other area, those applications. The final program includes 3 invited lectures and 108 contributed presentations of 3 days. This workshop will cover theoretical and computational and experiment, the study on the rarefied gas dynamics, the hypersonics, the micro and nanoscale gas flows and heat transfer, as well as emerging topics, the plume and the surface interaction in space, the Lagrangian method for the BGK method, the data-driven and the machine learning based on the mesoscaling modeling. We'd like to express our deepest thanks to all invited and the contributed speakers, especially session chairs. They did their homework in advance, and also staffs and the young research, also the student volunteers who made the Pre-RGD, the workshop, possible. The 32 symposium will be held next July, exactly 1 year later. But this is website. So it's nice pictures. But we miss travels. So we hope the situation improved enough so that everyone can be solved next year without much difficulties. So next, the overview of the program. So we have the 3 days. Each day we will have the 1 invited lectures. Begin with today's Dr. Laws. And each day we will have the 6 parallel sessions. For example, Boltzmann-related equations, and also hypersonic theory and simulations. So I'd like to introduce 7 session chairs. And the first plenary session chair, Dr. Mieussens. Are you here?
Yes, I'm here.
Yeah, he's here.
Thank you.
And Dr. Takata from Kyoto University.
Yeah, I'm here.
Yeah. And the Kong-Su again from Hong Kong.
Hi.
And the Elsan Ruhi from Jiatong University.
Hello. Hello
Yeah.
to all.
This meeting is being recorded.
And Seokbae Yoon, Seungkyungan University.
Oh, I'm here. Hi, everybody.
Yeah. The Vladimir Titarev, Russian Academy of Science.
Yes, I'm here. Yes, I'm here.
Hi.
And lastly, Ingrid Weisong, the Air Force Research Laboratory, United States. Are
I'm
you here?
here. Greetings, everyone.
Yeah. Actually, the idea of the having workshop this July, proposed by Dr. Ingrid. So we are really appreciate her devotion to the RGD community. Today, we are very pleased to announce the first Best Student Award. The session chairs for day 1, led by Dr. Kong-Su, selected the best presentation among 15 contenders presentations. So the first recipient is Mr. Schuller. Are you here?
Yes, thank you very much. It's an honor. Thank you.
Yeah, congratulations.
Thank you very much.
Let me read the certificate. The Best Student Oral Presentation Award for day 1 is hereby granted to
Mark Scholler, Yossard Pereira from Nera, France, and Luc Mieussens from Institut Mathématiques de Bordeaux, France.
for the outstanding oral presentation titled Analysis of the Intermediate Experiment Vehicles, IXV, Rarefied Aerothermodynamics. Ro Shin-myung, chair of this workshop, and Domenico Bruno, chair of IAC. So before we move to the first plenary lectures, this is another good news. The special issues on the recent hot topics in rarefied gas dynamics in the International Journal of the Computational Fluid Dynamics. As you know, the RGD Symposium has traditionally published papers in the American Institute of the Physics proceedings. So we'll do the same for next year's symposium, but nonetheless, this workshop will not publish any papers in proceedings, so that we propose the special issues in the IJCFD. So let me briefly explain these journals. The aim of the IJCFD is the continuous and the timely disseminations of innovative CFD research and the development, their application to a wide variety of fields. So we will welcome every presenters, especially the best student presenters. And we are targeting 5 or more papers. So the good thing about these journals is no page limitations. So submitted manuscript will be handled by primarily Dr. Kung Soo and together with me. And please submit the manuscript after the workshop before September 1st. So indicate the special issue, Pre-RGD32 workshop. So now the plenary lectures. So let me introduce the session chair, Dr. Luc Mieussens from France.
Yep, I'm here.
This lectures. Please welcome the Dr. Mieussens.
Okay, thank you very much, Roshin. Hello, everyone, and so welcome to our first invited lecture. I don't know if you can hear me. Yeah, okay. So this is my great pleasure to introduce Professor Li-Shi, who is a professor in the Department of Mathematics and Statistics at Old Dominion University in Virginia, USA. He's also a visiting professor in the Beijing Computational Science Research Center, where he will speak from today, I guess. Research interests of Li-Shi are kinetic theory and non-equilibrium statistical mechanics, numerical methods for kinetic equations, and kinetic methods for CFD. Okay, I have strange. Okay. If you have already worked on the Lattice-Boltzmann method, or if you have read a paper about this method, you have probably already seen the name of Li-Shi in the bibliography. Indeed, Li-Shi is one of the leading experts in this field. Well, so he will give many details about Lattice-Boltzmann in his talk, but let's say that this is basically a method to make numerical simulations of fluid flows, which is based on gas kinetic theory. So Li-Shi started to work on lattice gas automata and Lattice-Boltzmann when he was a student in the Los Alamos National Lab in the USA. And a few years later, in 1997, when he was a researcher at the IK's NASA Research Center, he started the collaboration with Pierre Lallemand, who is one of the inventor of Lattice-Boltzmann. This is when I personally met Li-Shi for the first time when I was a PhD student in Bordeaux, in France. So if you don't mind, I'd like to take a few minutes to tell a personal memory of Li-Shi at that period. I was working on numerical methods for rarefied gas dynamics, and Li-Shi had been invited by my advisor to give a seminar in our lab. Well, so at the time, Li-Shi was a young and enthusiastic and very sympathetic researcher, very happy to meet mathematicians and to explain Lattice-Boltzmann to other people. We have had long discussions about rarefied gas dynamics, and I remember very well he was so kind that he took time to read and correct my first paper. So this turned out to be crucial for my own career, and I'm very grateful to him. Well, almost 20 years later, Li-Shi is now one of the most famous experts of Lattice-Boltzmann for very various and important works like, for instance, physical and mathematical foundations of Lattice-Boltzmann and lattice-BGK, but also mathematical analysis like stability and convergence proofs of Lattice-Boltzmann to incompressible Navier-Stokes. And also he proposed many important improvements of the Lattice-Boltzmann method. For instance, he is the co-inventor of the MRT model, which is the most used version of Lattice-Boltzmann so far. And he also proposed numerical treatment of curved and moving solid boundaries and many other things. So Li-Shi published many papers, and some of them are cited more than 1,000 times. He is now associate editor of the Journal of Computational Physics and member of the editorial board of the Journal of Scientific Computing. But I think it's time to close this introduction, and now I ask you to welcome Professor Li-Shi. And again, Li-Shi, welcome to this RGD online workshop, and please, you can start your presentation on the saga of LB's quest for RGD ethics.
Can you hear me? First of all, I would like to thank the organizer for providing this opportunity And I'm grateful to my colleague and friend, Professor Luc Mieussens, to give me this kind introduction. I'm always grateful to that. Anyway, let me share my, where is the share? My screen. Oh yeah, here we are. All right, so can you see it?
Yes, we can.
All right, so I will also use this opportunity to say hello to my colleague and friend, Professor Paul Diller from Oxford. He is the true expert. And he will be my honest and kind critic. Okay, so today I'm going to stick to the theme of RGD, Rarefied Gas Dynamics, okay? So what is the effort of RB community done in this aspect? That's part of my talk. So here is my summary. I will talk about a little bit about the motivation of doing this, which is obvious to this community. And I will talk what is our understanding of two canonical flows. One is the pressure-driven Poisson flow, and second is the Couette flow, symmetric Couette flow. And I will talk about how we get the lattice-Boltzmann model and lattice-Boltzmann model in those two flows. And I will summarize my work, okay? So what is the motivation? Well, the motivation seems to be clear. I mean, in gas systems, when the density is low enough, you will have obvious, effect of due to the long mean-free path, okay? Now, and so Mieussens number is defined to describe this effect, so to speak. And then if you have a solid boundary, near the boundary, and in roughly the extent of the mean-free path, whatever that is, I'm not going to give it a rigorous definition of it. You will have a region next to the solid boundary where the gas molecule boundary interaction or collision is the dominant physics effect, all right? And this is different from the quote-unquote hydrodynamic regime where gas-gas interaction is dominant, okay? So we want to make this distinction. And in this region, we call it, this layer, Mieussens layer. I'm just giving a very rough introduction because I assume you all know it, okay? So, well, we also know that the Mieussens layer cannot be modeled by continuum mechanics, continuum equations, whatever that is, and therefore it must be solved by kinetic equation or even molecular dynamics, okay? So the question is, can we model, simulate the Mieussens layer better, faster, and cheaper? And it's always motivation, right? And better, faster, cheaper than what? Than expensive solvers like DSMC or direct solver of Boltzmann equation. Okay, can we be efficient? Well, so objective is how do we cheat and get away? That's always my phrase. You want to cheat, you want to be cheap, and so you have to cheat. And the key is whether you can get away or not. And we will see, okay? Okay, so two flows we see often in textbooks. One is 2D, pressure-driven isosomal long microchannel. And this has been a well-studied case in the very beginning of the hype of microflows. I'm sure you remember that. So let me see if I can give you a summary what has been understood. You have very long channel. The channel length is L, and its width is H. You use H versus L, epsilon, this ratio epsilon, as a expansion parameter. And you begin with the compressible Navier-Stokes equation, and you define your Reynolds number, Mach number, and Mieussens number this way, okay? And the boundary condition is this one. slip boundary condition. Epsilon V is what is called the accommodation coefficient of tangential momentum, and it's assumed equal to 1. You can tune the Euler value, okay, but that's just a minor detail. Now you start with the compressible Navier-Stokes equation and you expand in terms of epsilon, 3 variables. Pressure along the center of the channel, and the streamwise velocity and spanwise velocity. If you solve the incompressible Navier-Stokes equation, P tilt will be a straight line, U will be a parabola, and V will be equal to 0. But in an incompressible Navier-Stokes equation with the epsilon as an expansion, well, P has a hump, V is a parabola still, but with a correction at the boundary. V, it's no longer 0, okay? It's a second, but it's a second order effect. Okay, so this is the result being studied and we hope to simulate, okay? Now, if you integrate the momentum at the exit, you will get what is called a mass flow rate. And this has also been taught very often because it has a Mieussens number effect, and often it's also called Mieussens paradox, because when Mieussens number increases at the beginning, it decreases, and then it's a nonlinear effect. But here, because I'm only doing it very in a perturbative way, so I didn't get a full solution. Okay, but the Mieussens paradox is another thing which has been well studied. Okay, observed. So this is our understanding of long channel flow. So the second flow I want to talk about is Couette flow. Okay, and the geometry again is very simple. You have 2 walls, top and the bottom, moving in the opposite direction. I'm only going to talk about the symmetric one, but it doesn't really matter whether it's symmetric or not. Okay, you can always scale it. Now the coordinate system is that the streamwise direction X, it's along the center line of this geometry, and the spanwise is Y. Okay, now this flow also been well studied, and we can formulate in a low Mach number, you can formulate the integral equation for the velocity profile. Okay, and since it's an integral equation, it's a mildly singular integral equation because of the kernel. This is Ablomovitz function, Ablomovitz function, and so you can see that in order to capture the quote-unquote the Mieussens layer, you must somehow capture the singular behavior of Ablomovitz function. Okay, so I mean you can prove that, okay, well, velocity, because of that singular property of the kernel, the velocity profile has a singularity at the boundary. Delta is the distance from the boundary. Okay, obviously with this, you know that the derivative of velocity does not exist, but the velocity itself is well behaved because the limit of this exists when delta goes to 0. Okay, so these are the behaviors we want to study. Okay, it's a rather academic problem, and so with the mature theory of integral equation, you can prove all sorts of things, and then in solving the integral equation, you can see that because this K is appear here, okay, this, if you want to do it well, I mean, it has a huge dynamic range, this operator. And the difficulty, strangely enough, it's in small k, because K is 1 over K here in this term, right? In large K, it becomes easier problem, okay? But if you think about it, this is a kinetic problem. So if you ask the hydrodynamic guys to solve this problem. Obviously, small k, which is, you know, better approximated by the hydrodynamic equation, will be easier problem. But in solving the integral equation is the other way around. But this is just actually. So the point is that if we formulate an integral equation, we can solve integral equation very precisely with high precision, okay? And you can get very accurate answer. That's the message you want to give. So I want to just give the qualitative property of this flow. Now, near the center, the velocity profile is very, very much close to a straight line. Straight line is the Navier-Stokes solution. It's near the boundary there are some deviations. And this deviation increases as the Mieussens number increases, okay? So if I take the kinetic solution, which is a red line, minus a straight line from this point to this point, and then only plot the part which I would say is a kinetic component, you can see that this is a nonlinear behavior, okay? And this is the behavior we would like to capture if you try to solve kinetic flow. Okay, so these are the two things which I'm talking about. And so you can also see that this flow is relatively simple. It can very well approximate by polynomials, okay? Now, I'm moving to one of the things which I have been working on for years. And I don't know whether other than Paul Diller here, who else knows about this thing, that is Lattice Boltzmann. Okay, so I will explain briefly how do we get Lattice Boltzmann equation? What is the mathematical nature of it? Okay, so a little bit of theory. So now, let us start with the Boltzmann equation and linearize it. And the simplest linearized Boltzmann equation, model equation, is what is called BGK equation. It's a relaxation equation, okay? And I'm using this as a demonstration, okay? So F0 here is the Maxwellian. Now, as we know that if you are a hydrodynamicist, all you care about is the conserved variable, right? Equation satisfied by the conserved variables, which is mass, momentum, and the energy density, okay? So you write down the BGK equation in such a way that you can integrate along the characteristics. And this is exact, right? This is, you know, you can pretend you are doing ODE. You integrate along the characteristics. So from this equation to this solution is exact. There's no approximation is made, right? Now, you can then apply tail expansion on this. And the expansion parameter is this delta t, it's the time step size, and retain only the first order. So immediately you can see that you have an Euler type of scheme, right? Like this. And the truncation is anything delta t square has been truncated, okay? You can, of course, formulate different things based on this equation, okay? Integration over characteristics. I would like to mention that, you know, Professor Kunshu's gas kinetic scheme is also starting from this point, all right? It's just that he does not do all these expansion and did not do the low Mach number expansion. Therefore, his scheme is for compressible flow. Once you do the delta t expansion, you can also apply what is called a low Mach number expansion for the distribution function. And the second step is that we are not going to do the full-fledged phase space. We have to discretize the velocity space in such a way that it is a very small phase space we retain, okay? And then you discretize the configuration space X in coupling with both the discrete velocity and the time step. And this is something special to the lattice Boltzmann. Okay, so to do the low Mach number expansion, what you do is that you do the Maxwellian. It's kz minus u square, right? You do the expansion, it becomes kz square minus 2 u dot kz plus u square. And it's those terms related to u. You do the Taylor expansion. You only expand up to u square. Okay? Now, you can ignore the u square term. Then the solver will become a Stokes solver. I'm just going to mention in passing. Okay. In the same token, the non-equilibrium distribution function will also be expanded in this form. But the coefficient here is not so simple. It's no longer the constant. For those people who are familiar with the spectral method for kinetic theory, this is familiar. Now, you can see that you can organize these four terms. This number one term is the first 0th order Hermite polynomial. And this is the first order Hermite polynomial in U, all right? But the coefficient doesn't matter. Then this is in fact the second order Hermite polynomial, okay? Now, in kz, okay? So, these Hermite polynomials are in continual variables, okay? And you can explain the same Hermite polynomial for the non-equilibrium part, and the coefficient will be these. Okay? So this is the first step, expanding distribution functions in U. And because you truncate high order terms in U, you assume U is a small variable. And that's why this is a low Mach number expansion. The second thing you do is that you want to preserve at least conservation laws. So in order to preserve conservation laws, all the hydrodynamic variables, rho u, and energy, it must be preserved. So these moments must be preserved, okay? So as I said, we don't want to treat continuous velocity space. We need to discretize the velocity space. So basically what we are doing here is a collocation method. We are going to replace this integral, which are moments, okay? This is just moments, with a sum. And thanks to this Gaussian weight, the best way to do this is the Gauss-Hermite quadrature, right? In 1D, okay? And so, excuse me. Okay, so now, so in this case, we have to preserve how many moments? We have to preserve 0 order, first order, and second order moments. These are conserved variables, okay? So if you are in one-dimensional space, you have three, you can have 1, 2, or 3 points, right? And if we have 3 points, we can preserve second order moments. Okay, so these are just basic algebraic integral manipulations to tell you that if I start in 2D, okay, what kind of quadrature I have to use? And you have to choose what coordinate system you're going to use. So let's make that, for instance, if I want to choose Cartesian coordinates, meaning X and Y are orthogonal coordinates, okay, in 2D, X and Y, then I can decompose that integral in product of 2 integrals, okay, and each I can use 3 points because I know 1 point is not enough, okay? If I do that, then the result is that in both x and y direction, I have 3 discrete velocities. Is this clear? And the vector product of this result is it gives me 9 velocity in 2D. Okay, so I'm only doing these manipulations to show you that I can obtain with Cartesian coordinates, 9 velocity model with 0 velocity at the center, plus minus 1 at x direction and y direction, and plus 4 corners. Can you see that picture? If you cannot, I'll show you the picture. This is the picture. For each space point, the velocity space is discretized into this small set of discrete velocities if my condition is that the conserved moments as well as the fluxes has to be preserved. All right. Now I have a second choice. If I choose, instead of Cartesian coordinates, I use the polar coordinates. That means rho and theta. What I will obtain is triangular type of velocity. That means 0 velocity at the center and evenly distributed 6 velocity along a unit circle. Now, both these discrete velocities can be tied into a infinite lattice. It's a lattice structure. You can see that, right? And these are only 2 choices I have. If I want to preserve a lattice, structure. Do you have any questions? Well, great. So I'm going to talk more about this 9 velocity model in 2D, okay? What is the equation? There is something called Gross-Jackson model, right? That means you can choose infinite many eigenvalues as you want. This is, very simple theory. So in the lattice Boltzmann model, you can do the same thing, because what you do is that you choose those orthogonal polynomial on the discrete velocity, and you can tune their eigenvalue individually. So here is the model in a form. Okay, you still have this Euler type of, 1 time step and then minus this to the original point. But here is you map into the moments instead of a distribution function. And this is the equilibrium moments. Then you relax them with a diagonal matrix with individual eigenvalues, for which the conserved mode has eigenvalue 1. And for the non-conserved modes, the eigenvalue is not equal to 1. Okay? And these equilibrium moments, just rewriting the expansion we had before. The equilibrium, you can expand the Maxwellians in U, and then you write it down like this. Okay? So this is the model I'm going to use. Now there's another thing called entropic model, and I'm using the ancient model, okay? Because it's been shown that if you use this equilibrium, you somehow can have an H0. And one of the things distinguish Boltzmann equation from the hydrodynamics is that you naturally have second law of thermodynamics encoded in Boltzmann equation. And for a broken moment system, if you can preserve this, it will be a great benefit. So this is one of the things which, people propose, okay? So now I'm going to just give some terminology, okay? there are multiple relaxation models which I talk about, which give you the maximum freedom of tuning the relaxation terms, meaning the dissipation in the model. And there are another model which only use 2 relaxation parameters, one for even order moments and the other one for odd order moments, okay? And this is the minimally required if you want to get the boundary conditions correct, all right? And the simplest model is that all relaxation time are 1 over tau, which is called the lattice BGK. And in addition to that is lattice BGK with a special equilibrium, which I just mentioned, which claim to have H theorem. Okay, so these are the models we have seen, okay? And you can do careful analysis to see that the shear viscosity in the model is related to the relaxation time for the second order moments, which correspond to stresses, the component of stress, and the bulk viscosity is corresponding to, I think I made a typo here. This should be a moment, a relaxation time correspond to the diagonal moment, the energy mode, so to speak, the second order moment. And if you use the lattice BGK, you have only 1 parameter. And what you can see is that the bulk viscosity is small. And so when you simulate high Reynolds number, which you require low viscosity, and it's easy to instigate the disturbance due to the density fluctuation. Okay, this is one of the things we can mention. So now I'm going to use this simple-minded model. Okay, how simple is this? We have discretized 2-dimensional a plane velocity space to only 9 points. Okay, so it is drastically reduced the degrees of freedom. Okay, and we are going to solve this for first case is channel flow, and second case is the co-ed flow. Okay, see what we can get. It turns out that if I assume that span-wise velocity is equal to 0, I can solve this algebraic system analytically. And this is the solution of span-wise velocity. Is there any questions? Okay, so let me point out to you what this is. This is rho multiplied by velocity, so the momentum, okay? So the first term, this term, it's very simple. It's what you're familiar with. It's a parabolic, right? Parabola plus a constant term. And this constant term, depending on how you implement your boundary condition, that's number one thing I want to point out to you. Now, this is a pressure-driven flow. So this Umax is this constant force multiplied by h squared divided by mu. This is the exact formula you will get if you solve incompressible Navier-Stokes equations. Okay, except that you will get this US equal to 0. The other thing you can see is that if you have ny point of nodes, then your channel with h should equal to ny. This is a node-based method. So the node is in the center of a grid distance, so to speak, okay? And the boundary condition for, let's say, if you want to set this US equal to 0, then the boundary condition for this to be a perfect parabola is satisfied at half grid spacing, this half, beyond the last fluid node. Okay, so the question is, what are these quantities, US? Okay, and this is analytic solution, we can get it. Okay, so one of the things you can demonstrate is that there is a very commonly used boundary conditions called bounce back. Particle hit the wall, reverses the momentum, turns back. And you can show that this is basically equivalent to diffusive boundary condition in kinetic theory. Okay, there are other type of boundary condition, but you can solve it all. Okay, and then give that slip velocity. Okay, so once you understood this, you can see that the slip velocity depending on two relaxation rates. One is the one which determined by the shear viscosity. The other is the one which related to bulk viscosity. Okay, now because of this was first discovered by Ginsburg and others in 90s. So they said, okay, well, this is the basis for what is called a two relaxation model. If I can, because the shear viscosity is fixed, if you fix the Reynolds number. So so this is given, but this is an extra degrees of freedom can be tuned. If I can tune this as Q, such that this term disappears, then I have a consistent solution with the incompressible Navier-Stokes equation. And because I require 2 degrees of freedom in terms of relaxation time, that's why this is called TRT, 2 relaxation time model. Okay, so this problem is solved. Now, you can combine various boundary conditions, but my key message is that all these things can be solved analytically. Okay, now, so one of my warning to you is that large percentage of paper published in the lattice-Boltzmann community is the lattice BGK. And if you ask me why, I will tell you it's because most people are lazy. Okay, because if you can have a simpler model, why not? You know, MRT, multiple relaxation time model, will require 3 or 4 or 5 relaxations. This only have 1, why not? Okay, so if you have my analytic solution, then what you can see is that you can integrate the velocity profile at the entrance, at the exit of the channel, and divide by the standard Navier-Stokes mass flow rate, and then you can get this relationship. Okay, let's look at this closely. First of all, let's look at the definition of quote-unquote Mieussens number in this business. The key point I want to point out is that the grid resolution is a tuning parameter. And this is a nonlinear relation, okay? And therefore, you have a minimum. And this is often called a validation of lattice-Boltzmann capturing the Mieussens paradox. You see so many people publish on this. So the way I put it is, this is a fatal conceit, okay? You cannot have this as a tuning parameter, period. Okay. Now, if you use the MRT, then you can remove this effect. That's my message, okay? Because you can tune this, as I said it before, to make sure that the quote-unquote slip velocity at the end, that's a numerical artifact. Think about it, it's grid dependent, right? You're supposed to that grid size go to infinite. If you make this equal to 0, then you can obtain the correct solution. And so the other thing you must be careful is that when you do this simulation is that you must correctly implement inflow and outflow pressure condition, which must be consistent. You can impose the velocity profile, but you cannot impose the density profile. This is a subtle issue, okay? But it has been solved. So if we do all this, what you can see is that we can solve this flow with convergence result. And this is a demonstration of a consistency, okay? This is the compressible Navier-Stokes solution. And here's the comparison, okay? This is the pressure deviation from the linear profile. So we have the analytic solution, which I gave you, and the Lattice-Boltzmann solution. And the other dots, which are DSMC solution. With DSMC, you can get this, okay? And this is velocity profile. And these symbols are DSMC, okay? And the other one is the IP DSMC. And this is a small effect. This is span-wise velocity. You remember the V part is epsilon square effect. Epsilon is the channel height h divided by channel length. This is very small, and you cannot ask DSMC to ear this, okay? So this is Mieussens number 0.0, about 0.02. It's 0.0194. I didn't choose the number. I don't know why those people chose this number, but I just follow it. DSMC people choose this. This is one order of magnitude larger. It's 0.194. Same thing. Now that this is DSMC result. This is symbol is DSMC result. And again, this is the span-wise velocity, which we have no DSMC result because it's very weak. And here is the 0.388. This is the larger Mieussens number, in the transition regime. This is the red line is the Lattice-Boltzmann. The dot line, this is the broken line, is the IP DSMC, while this one is the DSMC. So you can see we are very, very close to the IP DSMC solution. Now, I want to show you how defective is the lattice BGK. Just look at this last figure. Can you see it? It's qualitatively incorrect. This is the velocity, not the velocity. This is the pressure. Okay, so the pressure is supposed to be a hump, but it becomes a concave like this. It's qualitatively incorrect. Same thing happened here. Although in a very small Mieussens number, it is qualitatively correct, but quantitatively not as good. So I laid the first case down. Number one, if we use the compressible Navier-Stokes equation to get this flow, the Lattice-Boltzmann equation can do a good job, but not lattice BGK. Done. So now, this is, I do a analysis why, lattice BGK is wrong. You can prove it is wrong. Okay, so let's go to the second case. How am I doing in time?
I think you can have 7 minutes more.
Good. All right, so that second case is the symmetric Couette flow. And we know that because of the symmetry of boundary condition, the distribution function must also have this symmetry. You flip the coordinate from the center, the velocity will change the sign, right? I mean, it's zero, it's symmetric about the geometry center. So if you consider this symmetry, then you quickly realize that the Hermite expansion I use, which is on the full range, is not good, especially when you are at the boundary. Think about it, at a boundary. If you have this symmetry, the Maxwellian at boundary is only have value above or below the boundary. I mean, inside the flow regime, beyond the flow regime has no value, right? I mean, think about that, okay? So we must construct a new lattice-Boltzmann model. And I'm not gonna go through detail because it will be the same. So what you do is that you must consider the expansion with the symmetry. So near the boundary, you have to use what is called the half-range Gauss-Hermite expansion. Instead of integrating from minus infinity to infinity, you integrate from 0 to plus infinity. So it's a half range, okay, to consider this, all right? So with this, you can again do it. So you remember this picture? Okay, so now, this is the nonlinear part of the span-wise velocity of the co-ed flow. Then you can see that, okay, we choose Mieussens number equal to 0.03, 0.1, 110, moving from this direction, okay? Now, when the Mieussens number is very small, you can just use in one direction. The key is in a span-wise direction, just for velocity point, you can do this good job. But if you in a large Mieussens number, you may have to use, let's say 30 or 40 velocity points. Okay? Here is the demonstration that in addition to the discretization of the velocity space, we also have to discretize the space, right? You can demonstrate that if you discretize the space finer and finer, the solution will converge to the integral solution, which we got. Integral equation solution, which is kinetic solution. You know, we can demonstrate that the simple lattice-Boltzmann equation model with very few discretized the velocity space, very small discretized velocity set can indeed capture kinetic effects. So done with my results. I think, you know, I'm going to come to the conclusion. So number one thing I want to give is that lattice-Boltzmann equation can be rigorously derived from the linearized Boltzmann equation. We can tell its kinetic root, okay? And I also want to mention that Paul Diller done a lot of analysis and proof in this regard, in terms of its accuracy and analysis and all, okay? Well, this is a question I like to pose to you guys. Is lattice-Boltzmann equation a minimalist kinetic model? You know, it is very simple. I mean, can it be simpler? Okay? With care, I mean, I emphasize this with great deal. With care, the lattice-Boltzmann is capable to simulate kinetic flows. And I also want to mention that Paul Diller also done some work to simulate some of these kinetic canonical flows. The other thing which I did not talk about is that there is evidence shows that lattice-Boltzmann may be a very efficient scheme for nearly incompressible flows, okay? And much remains to be done. This is an interesting subject. And thank you very much, okay? So please, if you have questions.
Thank you very much, Li-Shi. Thank you very much for this very interesting talk. So do we have questions here? So I'm just looking at the chat. So yeah, there's a question in the chat from Maxime Ziskin. Was multispaces version of lattice-Boltzmann studied? Where to start reading about it?
Okay, well, you can apply the same. Okay, the key is this. Lattice-Boltzmann scheme, you can always apply it to discretize the linearized Boltzmann equation, right? And linearized Boltzmann equation model indeed exists for the multi-species. So there are these models. there are quite a few papers. I published a few, and Pietro Arsenari also published a few papers. Published in, let me see, the journal is published in Physics of Fluids, Journal of Computational Physics, and PRE, Physical Review E. And you can write me email. I can provide you these references. By the way, let me see if I can go back. Okay, so just recently, Pierre Lallemant, myself, Krafchik, and Wenan Yong published a review on the memorial issue of JCP's 50 years anniversary, and it's a, it lists quite a, almost 500 references. You can find something there.
Okay. Do we have other questions or comments? You can ask your questions in audio. But well, I don't know exactly how to manage a session with 150 people like that. But okay. Let me check in the discussion in the chat. No more questions. So please do not hesitate to ask your question directly right now. Okay, question by Paul Delon. What does the velocity gradient near the wall look like?
A tough question. I did not compute it explicitly, but what I expect is this. I will never get the singularity. I will never get infinity, but for the large Mieussens number ones, I will get a pretty good solution.
Thank you.
Okay.
Because we do have a good convergence in two things. One is if you increase the discrete velocity, you will do better. If you increase the spatial resolution, you will also do better. This is a steady flow problem. So we do both these values, and then you can get pretty good solutions for that. Okay, so here is another one for Couette flow. Will pressure be uniform across the channel? I thought that, let me think. I saw the pressure, if I remember correctly, for the integral equation, it was a constant. Was it, Paul?
Correct flow, yes, I think it should be.
Yeah, it's a constant. And we did get that when we solved the solved the integral equation. I didn't present, but you can check. Let me see which paper. Okay, here, this paper, reference 4 by Li, myself, and Jie Shen, Computer and Fluids, 2015, plus this paper. No, not this one. This is repeat. This paper, JCP 2016. This gives a lot of mathematical proofs, what the solution looks like, so on and so forth. Paul, you see this? You are talking about this U prime, right? This does not exist.
That's right, yes.
And I'm absolutely sure that I cannot get infinity because I'm using a very simple polynomial to approximate x log x type of thing, What can be done is this. If I keep refining it, I will get a very accurate solution. We can show that. But not exactly, log at. You have to get very close.
Thank you. I knew that was a
Density-
nasty question.
Pardon?
You're saying I knew that was a nasty question, but I thought you'd
Oh, well,
appreciate it.
what's good friends for? How to decide what boundary condition to be used among various existing models? I mean, what model we are talking about? You're talking about that as Boltzmann? I always prefer bounce back because I can do a lot of proving. Okay, so the question is this: if you have the boundary which cannot locate it at exactly half point between two grid points, then you have to use interpolation again. That's good enough. Okay, so that next question: how does density profile will vary in micro scale flow? Which flow? Are we talking about the long channel flow? Kuwait. The Kuwait one, I didn't look at that. The pressure, no, I did not look at it. I forgot. I can get a solution. What are the key issues, constraints that will exist in application of LBM to low speed and high speed problem? Well, low speed, the question is whether this is a efficient solver or not. It's purely computational efficiency. All right. You are trying, you can show that this is a finite difference artificial compressibility model. So depending on, it's purely computational efficiency. High speed, so far, I haven't seen much success. But Paul, you may add, there are some models which will use the, you don't have to expand the zero Mach number. You can expand the locally non-zero Mach number and will improve this. So there are some work in this stuff, but it's not as rigorous as the low Mach number expansion.
Okay, thank you. Do we have further questions or comments? If not, I have one. Li-Shi, you give a very nice analysis of the behavior of a lattice Boltzmann for let's say not too small Knudsen numbers. So it seems it can work well, at least for velocity profile. In my opinion, there is a clear limit to that. When you take when the Knudsen number is larger and larger, so when you come close to the free transport regime, in my experience, you cannot expect to have a correct result with a discrete velocity method, and lattice Boltzmann is fundamentally a discrete velocity method.
So let me give an attempt. Okay, well, Mieussens number equal to 10 or something like that. Would that be good enough, large enough? But you see, we know that if you are purely a transport equation without a collision term, the solution is like exponential type of thing, right?
Mm-hmm.
Good. I would think that exponential function is pretty easy to be approximate. You think about it that way. I mean, let's think about it. What the solution look like, what kind of function it is.
Yeah, but what I mean, this is something which is well known, for instance, in linear transport.
This is not exactly same as discrete velocity model. If you think about this way, I will say this: we may have the similarity in terms of choosing the velocity set, but numerically, for instance, we do those Mach number expansion and all that. None of that is in the discrete velocity.
Mm-hmm.
So, I think Mach, k equal to 10. This is pretty large already.
Yeah, that's true. Okay.
Yeah, and then so we still can do it.
Okay.
At least for the velocity profile.
Okay, so thank you, Li-Shi. Do we have other questions?
Is asking what about the future of the LBM? Well,
this will be
the RGD guys, I suppose, like my good friend Professor Kunshi would like to kill us and eliminate us. I don't know. How long can we survive? I'm very fortunate to come here to give a talk.
Okay, thank you very much, Li-Shi. I think we can stop here. There is a 10-minute transition to switch to parallel sessions. So
Thank
thank you again very much, Li-Shi, for this wonderful talk. And
Okay.
everyone to attend this session.
Anybody want my slides, write to me. I'm happy to send it to you.
Thank you.
Before we move into the parallel sessions, I'd like to explain one more thing. Just wait. The survey. So after the workshop, we like to have your feedbacks to improve the next symposium. In particular, the question, the 7, you want to estimate how many the presenters will submit their manuscript to the IJCFD, the number 7. So if you are interested, please leave your name and email address. And question number 9 is about next year's symposium. So let's suppose that symposium will be held in the hybrid form. That means in person and also online. Then how would you like to participate? Let's say on-site to the Seoul or remote or the both, depending on situation and so on. So we will send you the email that this weekend, or you can visit the pre-RGD workshop, and then there is the first pages. You can find those surveys. So please feel free to respond to this survey. And then lastly, I just briefly mentioned the presentation guide before we move to the parallel sessions. So I know the 10 minutes is very short. So the presenters can use, let's say, from 3 minutes to 5 minutes. If you don't expect too many questions, maybe you can use up the 5 minutes, but make sure that you complete your presentations for 9 minutes. So we need 1 minute for transition. So finally, I'd like to thank all of you again for joining this workshop. So stay in the Zoom. Okay, it's break time.
The recording has stopped.